To understand how C++ works at a low level, we have to look at the most common feature of object-oriented programming: polymorphism. We use it every day, but rarely do we stop to ask how the CPU actually executes it. Let's look at a standard example. We have a base class called animal. It has a single function: speak. Notice the virtual keyword. This tells the compiler that this behavior can be overridden by children classes. Now let's create a derived class called dog. The dog class inherits from animal and provides its own specific implementation of speak. This is standard C++. Now let's look at how we use this. This is where the mechanics get interesting. We create a pointer. The type of pointer is animal. However, the actual object we are creating and pointing to is a dog. When we execute the speak function, the program correctly prints woof. It calls the dog version of the function. This seems obvious to us as programmers. But pause for a second and think about this from the compiler's perspective. The compiler reads your code top to bottom, translates it into machine instructions, and when it reaches this specific line, it hits a problem. The compiler only knows the static type of the variable. It sees a pointer to an animal. It does not know if that pointer holds a dog, a cat, or just a plain animal. So it is impossible for the compiler to know the true identity of the object at compile time. Yet the program still works. To understand how it works, we need to contrast this with a normal function call. This brings us to the concept of static binding versus dynamic binding. Let's look at what happens without the virtual keyword. In this scenario, we have a concrete object called A. When we call speak, the compiler knows exactly which function we are talking about. It knows the memory address where the code for simple animals speak lives. And because it knows the address, the compiler performs static binding. It essentially hardcodes a jump instruction to that specific memory address. Here the compiler cannot perform static binding. It cannot hardcode a jump to animals speak either, because the function might be overridden. The compiler is forced to use dynamic binding. Since it cannot know the address of the function now, it generates code that will look up the address later at runtime. The compiler generates instructions that effectively say, go to the object pointed to by pointer. Inside that object there is a note. Read the address written on that note and then jump to that location. For this lookup to work, the object itself, our dog instance sitting on the heap, must be holding that note. It isn't just holding its integer data members like age or weight, it is secretly holding extra information to help the program find the correct function. Let's look at the memory footprint of a standard class. We will use a struct called simple with two integer members a and b. On a standard 64-bit system, an int is 4 bytes. Since we have two of them and no virtual functions, we expect the size of this struct to be exactly 8 bytes. The member function does not affect the size of the object because code lives in a separate memory region, not inside the object instance. Now let's verify this by printing size of simple. This is exactly as we expected. The memory layout is just A followed immediately by B. Now let's create a second struct called polymorphic. We will give it the exact same data members, the two integers, but we will add a single virtual function. We haven't added any new variables. We only added the virtual keyword. Logic might tell us that the size should still be 8 bytes. However, when we run size of polymorphic, we get a different result. The size has doubled. We went from 8 bytes to 16 bytes. This 8-byte increase is the concrete proof that the compiler has silently inserted a hidden field into our class. To see what this hidden field actually is, we can inspect the raw memory of a polymorphic object. We will create an instance, set the integers to values we can recognize, like 0xAAA and 0xBBB, and then cast the object pointer to a raw memory pointer to look at the bytes. When we print the contents of this memory, we expect to see our integers. But remember, the object is 16 bytes long, which is enough space for two 64-bit values. The output will look something like this. At index 1, we see our data. The two 4-byte integers, 4a's and 4b's, have been packed into the second 8-byte slot. But at index 0, sitting at the very beginning of the object, is a massive number that we never wrote. It looks like a memory address. This is the v pointer, or virtual pointer. Every time you create an object of a class with virtual functions, the compiler silently inserts this pointer as the very first member of your class, pushing your actual data down in memory. So where does this pointer point to? It points to a static table generated by the compiler called the v table. Here is the architectural distinction that is crucial to understand. The v pointer lives inside the object. Every single instance of dog or cat has its own v pointer, taking up 8 bytes of its memory. However, the v table itself lives in a static, read-only memory. There is only one v table per class. So every instance of dog will have different memory addresses for their data, but their v pointers will all point to the exact same dog v table. Let's visualize the v table itself. It is essentially a simple array of function pointers. When the compiler generates the code for speak, first it looks at the object to read the hidden v pointer. Second, it follows that pointer to the v table. Third, it looks at the specific slot for speak. Let's say its index is 0, and it calls the function stored there. This design is why we can have a pointer to animal but execute code for dog. The animal pointer tells us where the object is, but the v pointer inside the object tells us what the object is. Now that we have seen the hidden pointer in memory, the best way to truly internalize how it works is to build it ourselves. We are going to leave the safety of C++ classes behind and implement polymorphism using plain C structs and function pointers. By doing this, we will see that the compiler is simply automating a very mechanical design pattern. First, we need to represent our objects. In C++, we used inheritance to say that the dog is an animal. In C, we don't have inheritance, but we have memory layout guarantees. We can simulate inheritance by embedding the base struct as the very first member of the derived struct. This layout is critical. Because base is the first member of dog, the memory address of a dog object is exactly the same as the memory address of its internal animal member. This allows us to safely cast a dog pointer to an animal pointer, just like the C++ compiler does implicitly. Next, we need to define the v-table itself. Remember, the v-table is just a collection of function pointers. We need a type that describes exactly which functions our animal supports. In our case, we only have one virtual function. It is called speak. Notice the signature of the function pointer. It takes a void pointer self. In C++, the this pointer is passed implicitly as a hidden argument. In C, we have to pass it explicitly. Every member function needs to know which object it is operating on. Now we need to update our animal struct. As we discovered in the previous section, every polymorphic object needs a pointer to this table. This v pointer is what makes the dynamic dispatch possible. Now let's define the actual functions. We need one implementation for the generic animal and one for the dog. These are just normal global functions. They don't belong to a class. Now comes the setup phase. We need to create the v-tables. Remember, these are static lookup tables. We only need one table for the animal class and one table for the dog class. These usually live in global read-only memory. Here is the most important part of the entire process. The constructor. In C++, you don't write the code to set the v-pointer. The compiler inserts it into the constructor for you. In our manual version, we have to do it ourselves. When we create a dog, we must point its v-pointer to the dog v-table. Look closely at dog construct. First, it calls the animal constructor, which sets the v-pointer to animal v-table. Immediately after that returns, the dog constructor overwrites that pointer, changing it to dog v-table. This explains why, if you call a virtual function inside a base class constructor in C++, it doesn't call the derived version. At that specific moment in time, the v-pointer hasn't been overwritten yet. It still points to the base table. Finally, we have all the pieces to perform the dispatch. Let's look at what speak actually translates to in our manual system. This syntax is effectively what the CPU executes. It follows the pointer in the object to the table, finds the function, and jumps. By writing this out, we realize that dynamic binding is just a pointer dereference. There is no magic lookup system or hash map involved. It is a direct memory access. We have successfully reverse engineered how virtual functions work, and we have built the mechanism ourselves in C. That brings us to the final critical question. Is this free? In software engineering, we often hear that abstraction has a cost. It comes from two specific sources, the cost of indirection and the loss of inlining. Let's look at the indirection first. When you call a standard non-virtual function, the CPU executes a relatively simple sequence. The CPU simply jumps to a known memory address. The instruction pipeline remains smooth because the destination is hard-coded. However, when we make that call virtual, we force the CPU to perform a pointer chase. To execute this, the CPU has to access memory 3 distinct times. First, it must fetch the object to find the v-pointer. Then, it must follow that v-pointer to fetch the v-table. Finally, it must fetch the address of the function from the table. This is dangerous for performance because of the cache miss. The v-table might not be in the CPU cache. If the CPU has to wait for main RAM to fetch that table, then it stalls. This can cost hundreds of CPU cycles where the processor does absolutely nothing while waiting for the data. However, modern CPUs are very smart. They have branch predictors that try to guess where the jump will go. If you loop through 1 million animal pointers and every single one of them is a dog, the CPU will eventually learn the pattern and predict the destination correctly. Then the cost becomes negligible. The performance really suffers when the types are unpredictable. If we iterate through this vector, calling speak, the CPU cannot predict the jump target. It will mispredict constantly. But there is a bigger cost than the pointer chase. The real performance killer of virtual functions is that they defeat the compiler's most powerful optimization. It is called inlining. Let's explain inlining with a simple math function. When the compiler sees this, it doesn't actually generate a function call. It creates no stack frame, no jump, and no return. It literally copy-pastes the instruction 5 plus 10 directly into the calling code. It becomes a single CPU instruction. Now consider a virtual function. When the compiler sees a call to this, it hits a wall. Since the specific version of compute to be called is unknown until runtime, the compiler cannot copy-paste the code. It is forced to generate a full slow function call. To visualize the impact, imagine we have a tight loop running 1 billion times. If compute is virtual, then the compiler has to generate a function call, a table lookup, and a return for every single iteration. We aren't talking about a 1% difference here. In tight loops with small functions, the virtual version can be orders of magnitude slower, purely because the optimizer's hands are tied. Virtual functions are not inherently slow in a vacuum. A single virtual call is only a few nanoseconds slower than a normal one. The problem is that they act as a barrier to optimization. So the rule of thumb is this: use virtual functions when you need architectural flexibility, like a plugin system or a high-level UI framework. But if you are writing a math library, a particle system, or a pixel shader, where every cycle counts, you should probably avoid them. In those cases, you should look at alternatives like templates. They give you polymorphism without the runtime cost. You have likely heard the rule: if you have a class with virtual functions, You must have a virtual destructor. Now that we understand vtables, we can explain exactly why this rule exists. Let's look at a class hierarchy that breaks this rule. Here, base has a standard non-virtual destructor. Derived allocates memory in its constructor and cleans it up in its destructor. This looks correct on the surface. However, the problem arises when we delete an object through a polymorphic pointer. When the compiler generates the code for delete pointer, it looks at the type of the pointer. The type is base pointer. Because the destructor in base is not marked as virtual, the compiler performs static binding. It effectively hardcodes a call to base destructor. The program jumps directly to the base destructor. It executes it and then frees the memory for the object itself. The buffer allocated inside derived is never freed, so we have a memory leak. To fix this, we simply add the virtual keyword to the destructor. By making the destructor virtual, we add it to the vtable. Now when the compiler sees delete pointer, it calls the virtual destructor. It performs the pointer chase. It goes to the object, finds the v pointer, looks up the destructor slot in the vtable and finds the address of derived destructor. The derived destructor runs first, cleans up the buffer and then automatically calls the base destructor. Finally, let's take a look at pure virtual functions. When we write equals to 0 in the function declaration, we are telling the compiler that this class does not provide an implementation for draw. This makes the class abstract, meaning we cannot instantiate it. But abstract shape still has a vtable, because derived classes will need one. So what memory address sits in the vtable slot for draw? It cannot be null, and it cannot be a real function address, because we didn't write one. The compiler actually fills this slot with a pointer to a special system function. This function will throw you an error. If you somehow manage to bypass the compiler's safety checks, usually by calling a virtual function inside the constructor or destructor where the object is only half built, you will trigger this function and your program will crash immediately. It is a safety net provided by the language runtime. If you get value out of this deep dive, do me a favor and check out the rest of the channel. We are building a massive library of modern C++ programming content, and your support really helps keep it going. I've put a video on the end screen that I think you will find useful. Click that if you want to keep going. Thanks for watching.